Welcome, everybody, to today's distinguished webinar series on artificial intelligence and cybersecurity. Today's talk is how to make a cyber-physical drone swarm, featuring Dr. Justin Bradley, Associate Professor of Computer Science at North Carolina State University. Prior to moving to NCSU, Dr. Bradley was a Richard L. and Carol S. McNeel Associate Professor of Computing in the School of Computing at the University of Nebraska Lincoln. He holds a BS in computer engineering and a master's in electrical engineering from Brigham Young University and a master's and PhD degrees in aerospace engineering from the University of Michigan. He's worked with Uncrewed Aircraft Systems since 2005, and he is a recipient of a 2021 NSF CAREER Award and is an Associate Fellow of the American Institute of Aeronautics and Astronautics. Dr. Bradley's research is focused on cyber-physical systems, particularly as it relates to control, autonomy, software, and computing for aerospace vehicles. Dr. Bradley, it's a pleasure to have you. With that, the floor is yours.
Thank you very much. Appreciate it. Let me share my screen here. That look right? Okay.
Yep.
Awesome. Thank you all so much for having me. I'm really excited to share some of our work with you and some of our research as well as our deployments with you guys. So as mentioned, I moved not long ago from University of Nebraska Lincoln to North Carolina State. And so I'm going to talk a little bit about some of the work that I did there at UNL, and I'm now continuing here. And really, I'm going to talk about, I want to discuss a little bit about what it takes to build a large deployable swarm that is AI powered and has emergent behavior as a result of sort of collective intelligence. I also want to talk a little bit about a specific research direction that we're working on right now that will, I hope, take us to the next level in that area. So I've been working with drones for a long time, both fixed wing and multi-copter. A lot of that work has been spent building drones that were able to interact in the environment, in the world in some way. So in this slide, I'm kind of trying to show you a smattering of some of the drones that we've built and deployed in the world for environmental monitoring, installing sensors into the ground, doing soil sampling, subsurface or water deployments, of course, swarms, and as well as prescribed ignition and tethered UAS are just a few of the things that we've worked on. My particular expertise is in the area of control, planning, and autonomy. And I've also recently been looking at more closely control software as it's sort of distinct from software engineering and control, but really the combination of those two things. So how control software on its own evolves, matures, changes, and can be shown to be correct. I've been doing this for about 17 years as a UAS researcher. And in my lab, we've got a full-time research engineer as well as a large handful of students. And we have an NSF-sponsored REU site where we have about 10 undergrads come from around the country to our lab to work on an undergraduate research project. So as a general sort of guiding philosophy to my research, this slide is trying to sort of indicate how I think what I value and I think what differs a little bit. So I believe heavily and strongly in the sort of foundational algorithm development that we've been working on as a community for a long time. You design things, you provide mathematical guarantees, and you simulate them, and you often publish them, and you may or may not really need to demonstrate these in the real world. As part of my lab, I've spent a lot of time building fieldable test beds, which allows me to identify deployment challenges, and I think as a result do more transformative research that allows me to transition that research directly into the deployment. And I think that that leads towards better outcomes. We've learned a lot about what it takes to deploy vehicles, including having started a company to do this. And there's a lot to be gained by learning how vehicles engage in the world. There's a different set of challenges, different sets of noises and uncertainty in the systems. And I think better research results from real world deployment. So I incorporate that as part of my research strategy. So I want to dive in a little bit into what is required for advanced swarming. If you think about swarms, I think the pictures in this slide are what you're probably thinking of. Animals do a really good job of this, and they really do this by following about 3 rules, and each agent sort of follows these rules on its own, and then the behavior that you see depicted in these slides sort of emerges as a result of that. And the rules are they move in the same direction as their neighbors, they remain close to their neighbors, and they avoid collisions with their neighbors. And the one big sort of overarching theme there is that you've got to know something about your neighbors. If you're an agent, you need to know about your neighbors and where you are and how you're moving relative to them. And that's a really hard problem, and it requires provably correct perception in the loop. We don't have that yet, especially with very small agents with extremely limited resources on board. So what do we do instead to build collectively intelligent swarms? Well, we've got GPS that's giving us absolute positioning and not relative positioning, relative to the neighbors, that is. And we use communication to communicate the information about the positions of their neighbors to every agent so that they kind of know where they are relative to their agent or their neighbors. And then we use decentralized control strategies, which require high rates of communication and possibly advanced control strategies if we can use them with the resources we have available. And then ideally, we would use formal methods in some way to avoid collisions and guarantee sort of provably correct performance. And there's a lot of challenges associated with that. So even though we don't have the perception yet, we could potentially use these other methods to do advanced swarming. But there's a fair amount of challenges associated with that. And I want to kind of talk about what I think the main challenges are and what we've done to try to address some of those. So first of all, as I mentioned, very insufficient onboard resources and communication. So we use on our small drones, and they're about 450 size, we use a Raspberry Pi, the latest version, pretty capable, not extremely capable. To give you a sense for what's possible there, real-time learning or vision probably isn't a reality at this size. With level of computing power, especially if you want to do anything else on there. And advanced GPS-denied navigation algorithms are probably infeasible. They require a lot of batch processing, a lot of state estimation and prediction that might not be feasible. For communication, we use an RFD 900 plus mesh. Because those radios are small and light and rather inexpensive, there are better radios. They cost a lot more, and I'm not positive you get a lot better performance. I think you get some benefits, but in our experience, a lot of the swarming functionality starts to break down around 10 vehicles. As soon as you have 10 agents roughly chattering with each other, the mesh networking starts to break down. In our experience, this is usually limits the communication to pretty slow rates. So, if you're in the business of designing decentralized control algorithms and you expect your neighbors to communicate their state information to all the agents at, say, 20 hertz so that you can do good decentralized control, you're going to have a hard time achieving that as the numbers of agents grow. I think the solutions to this are needing to rethink algorithms to consider resources from the ground up, and we need improved mesh networking and message protocols. One of the things that we've tried to do to fix some of that is tried to build decentralized algorithms that can trade off their computation and communication with their performance. So in this particular slide, I'm showing this is a consensus algorithm. It's information consensus. So we're just trying to get to consensus on, let's say, a sensed value of some kind. And we've designed this controller such that it's got one piece of the controller that pushes the rate of communication down, and then one that pushes it back up. And it does this in order to save bandwidth. So if you were to sort of communicate information at a fixed bandwidth, you'd sort of have this high blue line on the graph to the right here. If you sort of vary this and you can allow the agents to communicate less often as they get closer to agreeing, closer to consensus, you can save a lot of bandwidth, which is kind of what this video is trying to show. The next big challenge, I think, is decentralized algorithms. So if you're not familiar, centralized algorithms basically run on one machine, a ground control station, and it sends data to all the agents. Decentralized algorithms are individual algorithms running on every single agent, ideally the same algorithms, and then the data is shared amongst the agents in order for them to come to some agreement, and then behavior sort of emerges from that agreement or that decentralization process. Decentralization is, I think, the future. Centralized communication is good for now, but won't get us to advanced swarming. And that's because it has problems like a single point of failure. If the ground station goes down, you've got a problem. It also doesn't work that well with beyond visual line of sight, which is not only a regulation or policy problem, but also a technological problem. And so we need to think more about decentralization algorithms. Most of the work in this area has come from the coordination and control community. There are other areas that here that I think that I'm kind of listing: collision avoidance, formal methods for assured autonomy, and runtime monitoring, that I think are thinking about decentralized versions of those algorithms, but aren't necessarily yet deployed. As an example, I know that there is collision avoidance for based on reachable spaces for a swarm of agents, and it is decentralized, but has only been shown in simulation. So sort of taking that to the next level is going to be a challenge, which is something I'm going to talk a little bit about in a minute. One of the ways that we've tried to address this is by thinking about all of our controllers and all of our algorithms in a decentralized way. One strategy that we came up with is called hierarchical reinforcement learning. This builds on a popular area, which is learning as well as hierarchical control. The nice thing about hierarchical control is you can use existing control strategies to build these, and you can separate the controller, which is really one controller, but you can separate it into different aspects. So we built a control strategy that has a global controller together with a group controller. And the result of that is that with this one control gain, we can command groups of drones to go target different areas of an area. So follow a target or identify a target. And in this particular case, we only use learning to learn a control gain. The nice thing about this is that it gives you the ability to use the guarantees that come with control theory, but you use learning for kind of the hard part, which is figuring out the right set of gains. Another big one, I think this is perhaps the most often overlooked when people think about simulating their decentralized and other swarm algorithms, but don't actually implement them in practice. And that is all of the challenges associated with building, deploying, managing, simulating a swarm, and then taking it outside and running it. One way to think about this that I think is useful and instructive is that if you imagine that each individual agent has a success rate of about 90%. So let's assume that you have one agent, and that agent you have confidence will accomplish its mission with 90% confidence. If you then combine these into a swarm, the percentage that all of those agents are going to accomplish their mission drops to about 43%. So there's a very good chance, better than half, that you will lose an agent in a swarm mission. And that's meaningful and problematic if you expected them all to make it. Some people think of deploying the swarm for the purpose of having that additional redundancy. But the truth is, you don't know how many you're going to lose. And with each drone not having a high enough percent success rate, you're going to have difficulty having your whole swarm return or otherwise accomplish its mission. To make this happen, we've learned, you really need to meticulously manage hardware and software. You need to do this anyway for an aerospace vehicle. It becomes orders of magnitude difficult when you have replicated agents. So hardware management is really difficult. You've got to track mean time to failure of batteries, connections, crashes. You've got to track all this and make sure that you're aware of where the weaknesses might live. The hardware ought to be identical and thoroughly tested. We attempt to do that. And one thing that we've kind of a saying in my lab that has become really popular is that robotics is the science of cables and connectors. And so we spend a lot of time building, making sure cables are good, and connectors are connecting well and lubricated properly and taken care of. Procedures are also important. The aerospace world has a really strong tradition of utilizing processes and checklists to ensure safety and performance. And obviously, a real critical step in being able to deploy the swarm is making sure that whatever you put on the swarm is going to be successful. So having a simulation in there is a critical step if you want to reduce the mishaps of deploying a swarm. We've spent a lot of time thinking about this and built a number of tools to enable us to do this. As an example, we deploy all of our, we build Docker containers for all of our code. And that has a couple of real significant advantages. One is that it allows each agent to sort of download the changes, just the changes that it needs, doesn't have to download a whole new software package and recompile it on the agent itself. It's just ready to go in this container. It's already configured for you. Additionally, in our simulation tool, the sim tool that we built allows us to test the exact Docker images that we deploy onto the drones. So it means in simulation, we're actually exercising the exact code that we then deploy onto the agents. And it makes that process really seamless. Despite all this, and we have a number of other tools as well. For example, we have a configuration tool that sets a few configuration parameters for the drones and then pushes that configuration to all the drones. And then the drones know how to configure the individual things for themselves together with the broad configuration push that we sent. Despite all hardware consistency, configuration is still a challenge, but I think eased through some of these tools that we've built. Just a quick mention of our software simulator, our swarm simulator. So we built this out of the box to be targeted specifically for swarms. We built it to use either the ArduPilot backend built-in simulator, or it can use Gazebo, which is got a full fidelity physics engine as the backend. And this can be heavily customized. It's pretty nice because it runs in a Docker container and in a browser. So it doesn't need special hardware or software. It can just run on any browser where you can get that Docker container on there and execute it. And this makes it nice for deploying on many different kinds of ground stations, which we find really useful. And again, this leverages not only a container itself, but also leverages all the containers that we've built for the agents that we then push to the agents. So we literally exercise the code that we've already built and plan to push to the drones, which is pretty valuable. So we did all this over the course of several years, from 2021 to 2023, roughly. It led to a number of deployment opportunities. I'm going to show you one here. This is the day before Netflix came to shoot our swarm, which I'll tell you a little bit about in just a second. For this particular mission, what we have going on here is what we call aerial insertion. So we're attaching all the drones to a custom-made larger drone. That's a FreeFly Alta X in there. And then we've got the custom-made agents that are 450 size. So they all get attached to larger drones, and then we can fly them to wherever we like, and then we deploy the agents individually. The agents have leverage custom drop mode built on ArduPilot's row mode that they have. We call it drop mode. Put this kind of noisy there. So in this particular mission, after the aerial insertion, the swarm groups up and does what we just call a corkscrew loiter. So they just loiter around each other at different altitudes, make sure there's altitude separation. The larger drones have on board some machine learning-based classifiers that can identify drones moving in and out of the field of view. The more recent development on that front is that we can actually track individual drones. So we can identify a particular drone, not just a drone from the swarm, but which drone it is in the swarm. So that's kind of nice. It uses RGB as well as fused with infrared data. So as I mentioned, this was I did a news article with a local news station, and Netflix saw that, must have seen this, and I got a call from Netflix one day that they wanted to do a docuseries called Unknown, and one of the episodes was going to be about the intersection of AI and robotics, particularly in defense sectors. This research had been funded by the Army Research Lab, so we had them come out, and over several days they shot our swarm a bunch and took all that footage and built it into what became the rather unfortunately titled Killer Robots. But it is actually quite a good film. It's fairly nuanced in its approach to understanding how AI and robotics can come together. I'm not going to show the whole thing here. I'd really like to talk more about some of the research side. So if you want to go check it out, it's still on Netflix. If you've got a subscription, you can just search for Killer Robots, or Unknown is probably even better. So I want to move now on to a specific research area that I'm really interested in, and talk about kind of how I think it plays into this narrative of building drone swarms that are intelligent, powered by artificial intelligence, and are cyber-physical in their nature. And if you think about the artificial intelligence areas, this is one depiction. There's lots of ways to slice this, but just to give you kind of lay of the land here. So ChatGPT kind of lives in this deep learning area. Model-based reasoning lives in sort of the expert systems and robotics area. And I tend to be a fan of model-based systems. I think learning has its place, and I embrace that, but I'm a fan of models in part because you can make guarantees about them. You can make guarantees about optimality, you can make guarantees about performance, and that I think has value, particularly in safety critical systems, which drones are. So really quick briefing on automata, if you're not familiar. An automaton is an abstract model of a machine. It has states, transitions, and inputs, and its purpose is to return true or false, or accept, reject. A Markov decision process is a type of automaton, and it represents a sequential decision problem in a fully observable environment with Markovian probabilistic transitions and additive rewards. So all of this is to say that it's a stochastic automaton where the decisions are made according to what's best for maximizing overall reward or utility. You can do that by finding here, I've listed it, written it out. Here's the Bellman equation. If you form the Bellman equation, there are several different algorithms to solve the Bellman equation to give you an optimal policy. And basically the optimal policy tells me if I'm in a particular state, what is the action I should choose? And you're probably familiar, at least tacitly, with MDP because they form the basis for learning. When you use reinforcement learning, you're often learning directly a policy. rather than trying to build the MDP model and then solving that for the policy. You just learn the policy straight away, which I'm kind of trying to show in this plot or in this graph. Again, I like model-based reasoning, so I'm going to stick with the model for now. And what I want to do here is I'm going to try to build a model that I can change on the fly and solve it on the fly. But there's a number of issues. And so let me start with the first one, which is that oftentimes these types of models tend to blow up. Here's a real quick example. Suppose you had a multi-flight solar supplemented aircraft, and you were operating in a 10 by 10 kilometer area of operation. You divide that into 10-meter square landing zones, and the decision is whether or not to land and charge, or whether to, travel to the next location. And if you break this up into about 10-meter square landing zones, you end up with 1 million different states, 1 million different landing zones. If you break the battery charge up into 1% increments, so you know roughly what your charge is, to at least 1% accuracy, and you broke the time of day up into minutes, you very quickly end up with 144 billion states. So without a very complex problem, this is relatively simple as I've modeled it, you end up with an intractable number of states. So the point is that MDPs tend to have this problem where in real world problems that are interesting to roboticists, MDPs tend to blow up, and they also need global knowledge. There's some interesting insight, though, that comes if you start thinking about the MDP state spaces and the impact they have on policies. So, here, unsurprisingly, if you increase the number of states in whatever it is, number of charge states or number of day states, the time to solve sort of exponentially goes up. This is well known, not particularly interesting. What is interesting is that some states don't really contribute to the overall expected reward. That's what this plot is trying to show. You can see that for a number of charge states, it changes significantly. My total expected reward changes significantly. But for the number of day states, changing the number of day states does virtually nothing to change my expected reward. This suggests that some states matter more than others. And what would be really great is if we could sort of target those states or figure out which states might matter more than others. So the objective here that I'm going to try to come up with is to build a model-based robotic task planning paradigm that is able to be solved online, can be modified online, can adapt to environmental and mission uncertainty and changes, and is as close to optimal as possible. As soon as you start talking about online anything, you're going to remove global optimality. And so that's not surprising. So the goal is to get as close to globally optimal as possible. One quick insight based on kind of the plot I just showed is that it's not totally clear that every state matters, and you might be able to shrink that problem space. So if you do that, what you could do is bound the problem to a receding horizon and only worry about the states around me. In other words, I can't teleport the robot from one side of the room to the other without traveling through the adjacent spaces, right? Obviously. So there's no point really in looking much further down the line. What's most important are sort of the adjacent spaces. So we examine the nearby states, and we're going to rediscretize the state interactions where there is more value content. And we can do that because we're already keeping track of the value function if we started trying to solve the problem online. So we're going to look for where value is higher, and then we're going to shrink and expand the MDP as the robot moves through its space. So a little bit of intuition that I want to kind of try to give you here. If you think about just the continuous space, and let's say that at K% would be the threshold for deciding to stay in charge or move to another location. The problem is that if you discretize that space, you lose this information potentially. You can see that if I divide this space into 3, I've lost the information between this k% and where the boundary of my discretization was. So what's going to happen here is that I'm going to move to another location potentially at a higher charge percent than I would have if I'd had that information. And this changes with how you discretize. Some discretizations, as you can see, are better than others, and more isn't necessarily better. So you can see that for subdividing this space into 36 spaces doesn't really give me a better representation of this k% than n equals 10. So it depends on what the discretization is. If you expand this concept to a multidimensional problem, then you end up with these sort of hypervolumes of boundaries of where it's optimal to stay in charge or move to another location in this particular example. And so what we're really looking for here is, can I find good discretizations that give me increased information about the problem without having to model the full complexity of the problem, which, as I tried to show earlier, would lead to the state explosion problem. So 3 key innovations that we use to do this. We use the gradient of the value function to point us towards higher information content, higher value content. We then rediscretize the state space to try to improve the reward. And then we only do this within a receding horizon to make sure we keep that MDP nice and small. Quick example, to give you an idea of how this works. Drone sits at state 1. I'm going to split my states up and add new substates where I rediscretize when my value difference is greater than 1. And I've got a horizon of basically 1 state forward and back. So here, value is 2. I'm in, next state is 2. Previous value is 1. So 2 minus 1 is not greater than 1. So I'm not going to split. I'm just going to move. The next one, I've got 4 minus 2. That's greater than 1. So I'm going to split this state. So this tells me that there's potentially information hiding if I were to split up this state and rediscretize it. So I'm going to get, I create this new state with a value of 3, move to that state, and so on and so forth. Same thing in this next one, move to that state, and finally I end up in my reward, in my end final state. So how does this look? My goal is not to have you read through this algorithm, except to show you kind of the pseudocode that we built, or pseudocode version of the code we built, as well as mention a few key properties. This algorithm is pretty nice because it's model-based. It's got a few nice properties such that it's complete. So if there's a solution, it will find it. Even if what I call a flat MDP, which is like a fully modeled MDP, not being solved recursively like I'm doing here, but rather solved in all one shot. Fully modeled, full fidelity MDP. So even if you couldn't solve that MDP due to the state space explosion, our algorithm will solve it in this recursively optimal manner. Speaking of which, it is recursively or piecewise optimal. So it gives you that piecewise optimal policy, not globally optimal, but close in our testing. And it's fast because I can shrink and grow the problem in the space that within the computational resources that I have available. I can run it on virtually any CPU in real time. So really quickly here, I want to just mention a couple of nice results here. The problem of interest is a kind of a toy problem where I'm trying to move this drone to this goal. And what I'm going to compare against is a flat MDP, which again, this is the maximally discretized MDP that I can solve still in one shot. State space hasn't exploded too much, but gives me a good baseline for optimality. And I'm going to compare that against a constant receding horizon. So, maybe this rediscretization step doesn't really do anything. Maybe the real key is just this bounding of the horizon. So I'm going to kind of try to tease those apart. And a few details here of the MacBook Pro that we ran this on. So some pretty nice results here. So this is spatial complexity. So how many states, how does the state space blow up or not blow up? And you can see that for both a regular flat MDP and a constant horizon MDP, the state space really quickly blows up exponentially, as we kind of would expect it to, while the sliding mode MDP, that's what I've called these, so I call these sliding mode MDPs. The sliding mode MDP sort of stays pretty low, below a nice threshold here, based on the bounds of the resources that I have available in the computer. And same with the time to solve. So where a flat MDP or a constant horizon MDP is going to blow up in time to solve. Note that this is a logarithmic scale here. My sliding mode MDP or sliding MDP kind of levels off here to a constant solve time. So, and which I could reduce if I have fewer resources. And what really matters, just to make sure that it's clear that the policy is definitely what matters the most here. And our policy is pretty close to optimal. So here I'm showing the actual policy that results from solving that MDP. And the flat MDP is the optimal, fully modeled version, whereas here's the SMDP and constant horizon MDP. And you can see the only difference is these two policy, or these two, the action, the optimal action in each of these states is flipped. So very close, not only in expected reward, but also in the actual policy. This is very close, at least on the problems that we've compared this against. So a couple of really nice benefits that you get from this. You can solve MDPs of virtually any size. The policy is recursively optimal. And we've built some infrastructure that really lets you change the model on the fly. Because we rediscretize the state as we go, we actually change the MDP as we go. And so we now have infrastructure where we can change the MDP on the fly, which is leading to the next step, which is, could I then build the MDP on the fly as I go, adding new states, new information, new rewards, new actions as the drone encounters them? That's kind of the next step. So quick summary here. Deploying intelligent swarms is challenging. The details matter a tremendous amount. And I think this is what separates simulated algorithm development from algorithms deployed on real world systems. There's a lot of trade-offs and a lot of redesign that needs to happen to be able to deploy them. And these are things that you have to worry about. SMDPs are updatable, and this gives you a nice mechanism for solving large MDPs on very small constrained hardware. So with that, I want to just take a couple of minutes to say something about where I think swarms need to go, leave you with kind of a roadmap. And that the context for this is size, weight, and power constrained UAS. So this is a different thing entirely if your swarm is a swarm of global hawks or predators, where you've got a lot of computational resources on board. This would be a different calculation. So this is really, the context here is small constrained UAS. And in order to do advanced swarming, you really need to worry about health and aberration monitoring, solutions to the management of the software and the hardware, rethinking the algorithms from the ground up to consider constrained resources, and worrying about tracking and managing the swarm. I'm kind of trying in this bottom of this slide to kind of show you where I think we are and what it would take to get here. Right here, right now I think we're basically at very basic swarming behavior, where we have robust GPS, but it's not very good. Even if you can do RTK GPS, it's good, but you usually can't. We have intermittent communication and mesh networking that loses connectivity regularly and slows down bandwidth significantly. To get over here, what we need is more computation, better algorithms that continue, or that were built from the ground up to consider their constrained resources. And we need perception that can be put in the loop, in the control loop, in the autonomy loop, that can be shown to be provably correct, which is a very difficult problem. So with that, I will leave you with a few videos, and welcome to answer any questions.
Thank you, Dr. Bradley. Great presentation. I'd like to encourage all of our viewers to please post your questions in the Q&A. Can you go back to your roadmap? I was wondering, for increased computation, how much of that, like, to what like for example, NVIDIA Nano, to what extent could you increase your computation using small embedded devices with GPUs?
Yeah. Good question. So we actually run those on some of our other swarms, or some of our other agents. We actually run those in addition to the Pi, because usually we're dedicating them solely to some classifier, some machine learning based classifier, right? And it barely can keep up with that. The argument is a dangerous one, because there's always going to be faster computers with more computation that are going to keep coming out, more parallelization, et cetera, et cetera. What's unclear, though, is that the needs will go down as the computational horsepower goes up. It seems the other way around. We keep inventing and finding new uses for more computation. So I think what we really need here is to go back to the drawing board and think about, when we build algorithms, we need to think about constrained resources at the design level. That's the only real solution to that. So even though I'm putting here, yeah, we need more capable hardware, that is always going to be the case. That argument will always hold, and we will always be able to leverage more computing resources.
Okay, thank you. And then I was also wondering, on your swarm, the only way they're communicating positions is through the ad hoc network?
Yeah, yep.
Okay.
Yep. So they all communicate with each other. They are not, I mean, there's a different radio system that's sending just data telemetry to a ground station so we can track them. But all of the intelligence is emerging via them communicating amongst themselves. Yeah.
Okay, so that ground station it's not sending anything. It's totally
just monitoring.
Okay.
Yep. Fully decentralized. Yep. All the behavior is emerging from the decentralization. Yep. And the onboard intelligence. Yep.
Okay. I see we have one question from Narup. Thanks for your presentation, Dr. Bradley. In the context of swarms, can you comment on optimal task allocation strategies to minimize collective energy consumption?
Yeah, it's a good question. So I will comment by saying that there's some new work coming out from a colleague that I have here, and it's targeted at Ross, actually. So it's even targeted in the robotics domain. It should come out, I believe, in, I don't know, I can't remember which conference. I can dig that up. But there are people thinking, there are not very many people thinking about this, but there are some people thinking about optimal task allocation and how to do this in the context of real robotic deployed systems. The way that I think about this in my work has been more on the scheduling side. So I am working on developing schedulers for rate adaptive tasks. So rate adaptive tasks are tasks that have time varying periodicity. And there's some work that's been done in the engine control domain for ground vehicles, cars, that have done that with like one rate adaptive task. And I'm working on expanding that to a set of rate adaptive tasks. So by task here, what I'm talking about is a real-time computing task. So a block of code, not so much a sort of a robotic task, if you will. So just to kind of clarify terminology, but there are people thinking about this from the scheduling viewpoint, from this perspective of new task styles, new task constructs. Yeah, a few different options there. I hope that answers the question.
Yep. And then I guess one more from me. Is the drones you're using for the swarm, I saw two different types of larger ones and smaller ones. Is their battery life in the range of like 20 to 30 minutes, like a typical drone, or?
Yeah, good question. So the big one is an Alta X, and it is basically off the shelf. We've not modified that much, except for the landing gear was modified. And I mean, it's got some controllers on there to work with the landing gear, but it's otherwise off the shelf. And it has battery life unburdened at about 40 minutes, burdened even not very much. It gets to about 20 minutes. The agents are unfortunately a bit more disappointing. This is one of the issues is, you if you want to put anything on there to do some sensing or anything, you quickly run out of, you bite into your, flight time. So in our experience, our agents usually have around 12 to 15 minutes if we're lucky.
How much, if you just have the Raspberry Pi and RF module, how much does that decrease it?
Oh, that's a good. You mean from a payload perspective, right? I mean, its burden on power is on energy is pretty minuscule, right? The vast majority of the energy consumption is taken up by motors. So, we build custom containers for our radio and computer. So, and we build them out of lightweight carbon infused 3D printed plastic. So they're pretty lightweight. That only bites into the flight time like a minute or two. So it's not very significant. What's more significant is like any camera stuff and additional radios. So on these agents, which I could talk about more, we actually use two radio systems, one for inter-agent communication and one for just streaming telemetry to the ground station. And adding that extra radio, is unfortunately adds some as well, cuts into the flight
time.
So
if I understand you correctly, you're saying just the weight of the Raspberry Pi and the mounting brackets you think is more significant than the computation done by like the power required to compute?
Well, I hate to speculate. I haven't measured it, admittedly, so I better not state with certainty, but my current operating belief is that weight cuts into flight time more than computation by a Raspberry Pi. Now this changes with a Jetson. The Jetsons are power hungry, and so we actually often do a separate battery system for a Jetson when we do it, and that, as you might imagine, cuts into flight time a lot. But there's not much you can do if you want to run classifiers, neural nets on board a small drone. It's got to be a real thin net, or you've got to have dedicated hardware or something. They're just not capable of that much.
That would be interesting to see a comparison of with the extra battery. Does the weight, is the extra battery worth it when you the weight?
It's a nasty problem. Fortunately, LiPo batteries are energy dense, very energy dense. So that's nice, but it's still, they're heavy.
Okay, well, I don't see any more questions. Thank you for your presentation. You'll be seeing, you'll be receiving a plaque and a certificate from the Center for Cybersecurity for contributing to our webinar. I'm sure we'll also be in touch for collaboration opportunities. Our lab does
awesome. Would love to.
So,
thank you very much for having me.
It's been a pleasure. Have a good one.
Thanks. See ya.